Alright, let's do M. Again, very similar starting material, the same starting materials we've been using past couple problems. We have Cl2 in there, and our solvent is ethanol. Number of carbons, 1, 2, 3, 4, and 5. Nucleophile is the pi bond, attacks the chlorine, breaks the chlorine-chlorine bond. When the lone pair on the chlorine goes back around and attacks to form a chloronium ion. Cl. Right. Number of carbons, 1, 2, 3, 4, 5. We also made Cl minus, but we have a lot more ethanol in there. So the ethanol lone pair is going to end up being one. Actually, is the nucleophile in the second step. And we're going to attack carbon 2 because that's the most substituted carbon, the most delta plus carbon. The product we get here is trans. Again, alcohol giving us, and the product is going to be an ether plus Cl minus. At this point, you can think about the Cl minus coming around here, grabbing that H. And then the final product we get, let's number the carbons here again, 1, 2, 3, 4, and 5. The final product we get number of the carbons, 1, 2, 3, 4, and 5. We also made HCl, and our final product's an ether. Let's look at number N. Another one of these problems where we got to be careful because we're starting with the stereocenter. So we're starting with 1 enantiomer of the starting material. We're going to use H2 palladium on carbon. Now we don't need to know the mechanism for this one, but we do know that it's a cis addition. And since both these carbons are sp2 hybridized, it can attack from the top or the bottom. So let's number these carbons, 1 and 2. So there's actually 2 types of products we can make here. H. We're going to add H to both sides. This is carbon 1, this is carbon 2. We're also going to make the enantiomer. Well, in this case, it's going to be the diastereomer, actually, because we started with the stereocenter to begin with. So the H's could have came from on the top side, too. But because this carbon is already a stereocenter, that causes this new stereocenter on carbon 1, which can form a mixture of R and S, we form diastereomers here. Which of course means one stereocenter is the same, so this carbon's stereocenter is the same, and one is different. And then we form a mixture of diastereomers. So let's look at O. O has a cyclopropane ring, double bond. I'm going to react that with Br2. Number of carbons, 1, 2, 3, 4, 5. Pi bonds are a nucleophile, it attacks, breaks the bromine-bromine bond. The lone pair of the bromine comes back around and attacks carbon. So we form a bromonium ion. Number of carbons again, 1, 2, 3, 4, and 5. A lot of people want to do a carbocation rearrangement, but we of course do not have a carbocation, so we cannot do a rearrangement. That's the key point here. The key point here is no carbocation. We have a bromine, but no carbocation, no rearrangements. We attack the more substituted carbon, because that's the more delta plus. carbon 2. And our final product we end up with is the bromines trans to each other, plus the enantiomer. Okay, let's do P. Go cyclobutane. We have it react with H+. And our solvent here is ethanol. First thing we do is number these carbons. 1, 2, 3, 4, 5, 6, and 7. First step, pi bond attacks H+. And we make a choice where we're going to put the carbocation. 4, 5, number our carbons all up, 6, 7. Put our carbocation on carbon 2 because that's a secondary carbocation, more stable than a primary because of hyperconjugation. So what else do we have in there? We also have the ethanol in there. Now at this point we have to ask ourselves, can we make a more stable carbocation? We could do a hydride shift, but that would put a plus charge on carbon 3. That's only a secondary. Carbon 4 is too far away. It has to be 2 bonds away to do a hydride or methyl shift. Carbon 4 is too far away, so we cannot open that ring up. So the only thing we can do, have the ethanol attack. Oh, we have an alcohol. We end up forming, put a plus charge on the oxygen. Number our carbons, 1, 2, 3, 4, 5, 6, and 7. Whenever we have an alcohol as our solvent, we end up forming ether products. And our H here is a catalyst. So the final product will be plus H plus. So it's regenerated. Finally numbering our carbons, make sure we're not losing track. 3, 4, 5, 6, and 7.